Hello world, it's Craig. I have a good buddy Mark up in the Seattle area, and we have several common interests, and we regularly swap emails about this and that. When he saw that I was doing a series on the Digi-Key Nibbler, Mark surprised me with this document. Now this is a 2006 email request from a fellow named Andrew, goes by Andy, to Digi-Key for information about the Nibbler. According to the email, Andy's grandfather built a Nibbler, which is now long gone, and now Andy would like to write a little article on the Nibbler, and he would like to build one himself. So he is asking Digi-Key to share any information they might have. And unfortunately, we've not had any success following up with Andrew, who originally requested this document. Maybe somebody knows him, but we really appreciate him getting this much out of Digi-Key. And we also don't know if what this document is everything that Andy got, or if there's pages that were missing. But anyway, this is all that we have now. It's a dozen pages or so about this 4K or 8K RAM memory expansion board. Now this is mostly a narrative document. There's no schematics. The technical information is somewhat sparse, and occasionally it's even conflicting with itself. Now I will warn you that this video is not going to be everybody's cup of tea. I'm going to go through this document because I'm starting to reverse engineer this board so I can make a work-alike to go along with the work-alike Nibbler board that I made. And this is just the first step. And even when this video is over, there's going to be some more questions than what I have answers for. If you only want the answers, you may want to just jump ahead or wait for the next video. But if you have an eye for technical details and you have a deep interest, your input would be appreciated because there's a lot of gaps in this document, and your guess is as good as mine when it comes to interpreting their concept. So looking through the document, this is what we know, and I'll attach a link to this document in the description. Okay, on page 1, this is October of 1979, and this is revision 0. Remember that Digi-Key only advertised the Nibbler from June of 1978 through June of 1979. And by October of 79, they had quit advertising it in magazines, and I don't believe it showed up in their winter of 79 product catalog. So in my mind, there's a good chance that this board never actually materialized into a product, and it only got as far as this concept document. On page 2, we can see that it was sold assembled as either a 4K or an 8K board, and you can upgrade the board at a later time when you have the cache. The RAM is 4K by 1 bit, MM5257 static RAM. They say 5247, but in the board map, we see later it's a 5257, which I think is correct because the 5247 is a ROM. In the 1980 data book, it says that these outputs can be OR tied, which is really what I wanted to know. I suspected it, but it's good to know that these outputs can be OR tied because then we can just tie the two banks together and then buffer them onto the bus. Another thing it does say here is that each signal on the bus is a maximum of 2 standard bus loads. And I presume they mean standard in LS, not just standard TTL. So make a mental note of that because that gives us a bit of insight later with these buffers. Page 3 is the edge connector, the map, and they have an asterisk next to the signals that are used or generated on this memory board. And they've added 2 new power rails. They have unregulated 5 volts on pin 19 and 21, which we'll see we'll need later to power this RAM board. Now maybe it's an oversight, but they do say that the 5 volts and the ground are only taken from the fingers on the component side. They're not using the fingers on the solder side, which I'm hoping that's a mistake. But anyway, I'm not going to duplicate that. I'll take the power from both sides. Okay, the next page 4, they talk about the Nibbler onboard Deselect. This signal goes back to the Nibbler. It's generated on this board. It goes back to the Nibbler, and it has the Nibbler board deselect its own onboard memory when the address being accessed is above the bottom 4K. So when they designed the Nibbler, rather than completely decoding its own address base, they pushed that task off into the future and left it for other boards to do. So on this board, we have to have some logic that when the address is greater than 1FFF, then this board needs to assert this deselect line. And so it needs to assert that not just when this board is selected, but anytime the address is above the 1FFF. So the deselect line is independent of this board's actual address. Now there could be some signal contention if you have not properly strapped this and you have that deselect strapped in more than one expansion board. Technically, if there's multiple memory boards, each of them will be detecting the address and assert the deselect line the same, so any contention would be short-lived, but still. Personally, I would have made that an open collector signal to eliminate the potential for contention. And it would also eliminate the need for the jumper because each board could then just assert the deselect if it's being addressed. So there's this deselect label here, this jumper labeled E, and I'm presuming that that signal just goes to the jumper and then goes onto the finger, and the jumper is just removed to disable that deselect. I don't think that that deselect is being enabled or disabled with any of the logic. And if we look at where that line goes on the nibbler, it just comes in to enable the buffer. And if it's not controlled by another board, then this jumper has to be installed to take that line low and enable the buffer. So this is another place where we could have a problem if the user forgets to remove this jumper. It's hard tied to ground. A current limiter would have been a good addition here to offer at least a little bit of protection. And we have to remember that if we ever remove the memory card, then we have to put this jumper back on, or the nibbler isn't going to be able to access any memory. Now we get our first look at the little board here. And so we can see some of the chips and the jumpers that we have to work with. We've got two 81 LS97s, and each one of them is a dual 4-bit tri-stated buffer. We have a 74 LS10, which is a triple 3-input NAND, 74 LS27, which is a triple 3-input NOR, and a 74 LS85, which is a 4-bit magnitude compare, which has greater than, equal to, and less than outputs. Okay, next is page 5, where we get it was originally at one time the full board map and chip map, if the fax machine hadn't blacked out this part. But what we can see now is that there's also this address jumper. So we have address jumpers 12, 13, 14, and 15. So we can strap the address select. And also this is our memory up here, and these are the MM52, 57, 4K by 1 RAMs. Okay, the next page, this was page 5. Page 6 is missing. This is page 7. Talks about address strapping, but there's a big X across it. And this is an interesting read, but this isn't for this board. It looks like Digi-Key made or talked about making an analog to digital board. And that's what this address strapping document is about. It's for that A to D board. This is page 10, and this is the correct address strapping for this board. So what do we see on this? We see the upper 4 address bits are decoded, as we expected, and that all looks straightforward. And we saw that 2x4 header for the address with shorts on it for A12 to A15. Now we don't know any more about how this is working to match that address, but notice there's no pull-up resistors on these lines. If we go back to this board, it doesn't show any resistors here. Maybe it does have resistors, but they're not shown. So this address strapping, maybe it has resistors, maybe for pull-up, maybe it doesn't. But I would guess that they are hard tying the line to ground, the input to that comparator to ground, when the jumper is installed. And when the jumper is not installed, then they're just relying on the signal or the input to float that line high. So this tells us if it's an 8K board, it must be strapped to an 8K boundary. Okay, that's reasonable. And the board takes 2 pages of memory. Now, a page on the SCMP is 4K, as you might remember. And then they tell us if the jumper is in place, that matches an address of 0. If the jumper is removed, that matches an address bit of 1, which is what I already mentioned. Okay, the next is page 11. This is a memory map, but again, I don't think this is for this board. I think this must be for the A to D converter because they have memory mapped I/O down here in the first 4K. So I don't think this is for the memory expansion board. Now we're on page 12. This, I think, is for the memory expansion board again. We insert the strap to match a 0 address bit. When the board is at 4K, it can be mapped to any 4K boundary. When it's at 8K, it must be mapped to an 8K boundary. And that's nice that when the board, it doesn't occupy any more memory than what, or it doesn't occupy any more memory space than what it's actually providing. But allowing the 4K board on any 4K boundary is somewhat complicates the glue logic. They could have taken the easy route and just had the board occupy both pages, meaning it would occupy 8K even if it was only a 4K board. Or maybe it would just respond back with 4K and it would roll over the 4K in that 8K block. After all, one would have expected that the user would just populate the top 8K rather than put in two 4K boards. But they did the right thing and they made it so that it actually decodes properly 4K or 8K. Okay, that was page 12. Page 13, we're talking now about upgrading the 4K board to the 8K. And there's a few useful tidbits in here. We learned that the bottom row is the upper 8K. But I don't know which row is the bottom row because they don't say top or bottom anywhere else in the document. But I'm going to presume that this row that's opposite the fingers is the bottom row, because in the Nibbler, if you remember, all of the chips are inserted so that pin 1 is at this end by the fingers, and so I envision that they're looking at this with the fingers up, and then this is the bottom. But this gives us the steps to upgrade the 4K board to 8K, and it just requires adding the RAM sockets and the chips, and then there's a 5-volt regulator that you put in here, and then you change the jumpers. But also on this page that's interesting is this memory configuration jumper. And this is key information for how the board works. There's 3 here in the top row and 2 in the bottom row, and then they have little 4s and 8s. So there's a 4 between those, an 8, a 4 up here, and an 8 down here, and they have it shown for 8K, and the 2 jumpers are strapping the pads on the right. So I presume that for the 4K, we're going to take this top strap and move it to the left, and this bottom strap will then be vertical and connecting those 2 pads on the far right. Now on page 14, they fill in a few more details about the power for this board. They talk about this alternate power source. So the board can use onboard regulators, and power can come from an unregulated 6 to 12 volt rail on the bus. But when using the regulated 5 volt, so the 5 volt that's coming from that Digi-Key power supply we looked at before, then jumpers A and E and this 8K jumper over here are all inserted. So there's actually 2 E jumpers. This is the E jumper here for the power, and then there's the other E jumper here, which is for the Deselect. And if you're using the unregulated power rail, it says only jumper C needs to be installed, and these other 3 jumpers come off. So I'm guessing that this C jumper supplies the unregulated feed to both of the voltage regulators, which are like a 7805 equivalent. And then these jumpers down here choose between either the onboard regulator or the regulated from the fingers. The thing I don't like about this is there's a lot of room for misconfiguration. So on the board that I'm doing, I have this rearranged so that these selection jumpers for the power are mutually exclusive. So if you're powering one bank here, it can either be connected to the bus finger on the regulated, or it can be connected to the onboard voltage regulator, but you can't accidentally connect it to both, which is a possibility with the way they had the jumpers configured. Okay, now we're on page 15, and they show us the way the regulators are. They have a LM340T-5, which is a 7805. They don't show any jumpers. This is the unregulated input. They don't show any jumpers there. They don't show any jumpers here. But they do tell us that this regulator is the control logic and the first bank of memory. So that's on one regulator, and then the other regulator is for the second bank of memory. And this you have to populate yourself if you've only bought the 4K board and are upgrading it. And finally, this is the last page. Page 16 is the bus connections. And I mentioned in the last video that I thought the bus connections would be ad hoc, point to point. But this says that all signals are wired through. So this is indeed a full backplane bus, where pin 1, as they show here, is just daisy chained from the front to the end. And all the pins are just daisy chained from the front to the end. So this was a full bus system. Okay, well that's it. That's everything we know about this mythical Nibbler RAM 4K, 8K expansion board. But there's a few more details that we can assert just because they make sense. The input current of the 5257 RAM is very low, 10 microamps or so. Now that means that the input buffers on the data lines are not needed. So I don't think that either of these two 8187s that we see at the bottom of the board are being used to buffer the input data. And I don't think they're being used to buffer the incoming address either. Because remember, the address and the data was freshly driven by the 81LS97 on the Nibbler board. And those drivers should be sufficient to fan out at least 10 74LS devices and dozens of 81LS devices, or these high impedance input MM5257s. So if the low loading of the 5257 isn't enough reasoning, then it's a simple fact that there's only 16 bits of drivers total on this board, so there's not enough to do the 16-bit addresses and 16 bits of data that are going into and coming off of this board. So that, coupled with the fact that the drive current of the 5257 is also very low. It's only about 200 microamps. And since the 5257 has such a low drive capability, I think that we can safely say that one of these 81LS97s is used to drive data from the RAM onto this bus. And as I mentioned, this RAM can be wire OR, so I think one bit is just connected together on each of these, and then that bit is driven out, the 81LS97. Now, the claim to fame of the 81LS family, if it has one at all, is that it has a very low input current requirement, much lower than a typical 74LS device. An 81LS low-level input will take less than 100 microamps, which is about a quarter of the typical 74LS low-level input current, and an order of magnitude less than a standard 7400. So that's why they selected the 81LS drivers instead of just some 7400 drivers. They have a lot of drive capacity, they're tri-state, but they have a very low input current loading. So that's everything that I was able to glean from this document. Now I have a first version of the design completed, but I also had issues matching their selection logic, and I'll get to that in a bit. So on my schematic here that I'm showing you, I deleted my version of the selection logic because I don't want to contaminate your thinking. I wire OR'd the data outputs from the RAM banks and used one of those 81LS87s to put the 8 bits of output data onto the bus, like I mentioned. And that's enabled during the read strobe when either one of the memory banks is putting data onto the bus. And they said in the electrical characteristics that no signal was more than 2 standard loads, so I used the second 81LS97 to buffer the inputs, like the high address nibble, where the fan out would have been more than 2. Then I used 2 more bits of that buffer for the read and write strobes, since those need to be well defined and it wouldn't hurt to clean them up before we send them onto the RAMs. And of course that read strobe has to be gated with the select. Then I used another bit of the 81LS97 to drive the deselect line back onto the bus to deselect the Nibbler's onboard 4K RAM or memory. And in this design, I'm going to live with the board address inputs to the comparator not having pull-up resistors. And I just let them float up when the jumper is removed. Now, I wouldn't do that myself, but since it's an LS device, it's going to have a 15 or 20K pull-up resistor internal to that device on the inputs. So it will pretty firmly pull those devices up. Now, some comparators, of course, have an explicit pull-up resistor on the inputs, but this isn't one of those. So here we're just going to let those float up. I thought about putting in a little resistor pack here, but it's not going to hurt anything to do it this way, and just going to call it good enough. So back to the problem that I was having that leads to this call for idea for inputs. Now I may just be daft, but I came up with a few configurations of the select logic, but I cannot match their gate requirements. And in my current effort, rather than a triple 3-input NAND, I need to use a quad 2-input NAND. And it fulfills all the requirements. My logic allows the board to occupy 4K boundaries when in 4K mode and 8K boundaries in 8K mode as they required. It generates the Deselect signal anytime the address is above 1FFF, independent of the board's selected memory range. And of course, it gates the read strobe with the board select, so the output buffer is only enabled when this board is being read. And I spent a fair amount of time looking for other options, but I couldn't make it fit with that other triple 3-input NAND. Now keep in mind, we don't actually know if it can be done with these chips because we don't know if this board was actually built or if there is a revised document that's yet to be found. So, maybe this doesn't even work this way. But hopefully somebody out there can come up with whatever design Digi-Key must have had in mind when they picked these chips. Okay, well that's it for this video. I'm forging ahead with the board design and layout as I've got it, but I wanted to do an update video on the Nibbler, especially because I'm getting lots of questions regarding when the Nibbler work-alike boards are going to be available and ready. And the answer is that just as I was about to submit the Nibbler board for fabrication, Mark sent me this document, and so now there's going to be this delay until I can submit both the Nibbler and this memory board together. And now that I know that it's a backplane bus, I need to also submit a backplane board to connect them all together. So I'll be back when I have more to say about this, and I'll put this document up on the project page as I mentioned, and I'll put a link to that in the description. Oh, there is one more tidbit if you're watching until the very end. If you're interested in these projects and you're starting to look for chips, I noticed that Elliott Electronics in Tucson, Arizona has the INS 8060 SCMP processor listed on their site for $5. Now the INS 8060 is the one that's used on the Nibbler board. They've also got these MM5257 4K by 1 static RAMs for $2.95, which is another bargain. And they have the 81LS97s. They're listed for $695, which isn't the best price. And you can use the 74LS replacement for the 81LS. They aren't as good in terms of the input loading, but I'm sure they'll work in this application. We've only got a few boards in our system. And also for the Nibbler, and at least with the design that I have for this memory board the way it is now, the octal version, the 81LS95, also works because they're enabling both halves at the same time whenever they use the 97. So if you can find the 81LS95s, those work just fine and they tend to be cheaper. But at Elliott, right now they've got the price on the 95s and the 97. It's the same at that $6.95. Well, that's your reward for watching until the end. If you need to go chip shopping, Elliott's got these for very reasonable prices. Well, thanks for watching, and remember that this channel is not monetized, and it's entirely fueled by likes, shares, and viewer engagement. Talk with you later. Bye-bye.